we're going to talk about concavity. Concavity involves the second derivative. As I wrote it there, it's not called the second derivative test. It is called the test for concavity. The second derivative test, something we have not mentioned right now. And basically all it does, the second derivative test is another way of doing the first derivative test. Another way of finding out the same information as the first derivative test using the second derivative. That's not what we're going to do right now. We're just going to test for concavity, which happens to involve the second derivative. Why? Because, first of all, f prime of x. If f prime of x is positive, so what does that tell you about original function? Increasing. It implies the original function is increasing. Okay? I wrote this a minute ago. I just want to reinforce this because it has to do with the second derivative. F prime of x is negative. It means the opposite. It means the original function, we now know that it is decreasing wherever that is happening. Okay. So now, whatever the first derivative tells you about original function, the second derivative must be telling you that same thing about first derivative. Because the second derivative is the first derivative of the first derivative. Does that make any sense? All right. Meaning you could easily replace these symbols. I could just add a tick mark here and a tick mark here, tick mark here and tick mark here. Oh, not over there. There. Agreed? That would have to be true. The second derivative is first derivative, first derivative. First derivative tells you where the other function is increasing. So second derivative, if it's positive, it tells you first derivative is increasing. What does it mean for the first derivative to increase? What does that tell you now down the chain about, you want to know about original function we're trying to get at here. If the first derivative is increasing, then that means the slopes of original function are getting larger, correct? F prime is slope, so it means slopes of f, the original function, are getting larger. They're increasing. Or the slopes of original function f are getting smaller. Not that they're positive or negative. No, we're not saying the slopes are positive or negative. The slopes are either getting larger or the slopes are getting smaller. It doesn't tell you about their sign. Okay? So what this translates into is for original function f, I'll just without the coordinate axes. So if the slopes of f are getting larger, right? Then wherever I start drawing the curve, if the slopes are getting larger, if I should start here per se, right? If I were to draw the curve like this, would you agree, let's say that's our curve for right now, would you agree the slopes of this curve are getting larger? Well, yeah, they're starting out, right, the slopes here, the slope there, starting out negative, it's becoming less negative, you know, now it's going positive, more positive, more positive, agreed? The slopes are getting larger. They don't have to change from negative to positive, they have to get bigger. They could always be negative, but become less negative numbers. They could go through zero, they go through a horizontal tangent, and they keep getting larger. They could start at positive and keep getting more positive. Okay? So what this is going to be called is concave up. That's the appearance the curve takes, right? The normal idea of concavity, like of mirrors or whatever you have, right? Lenses. Or lenses. Is this particular construction. And what it really means is that the slopes are getting larger. And the other way of describing it is tangent lines lie.
What?
Tangent lines lie below the curve.
Oh.
So they're lying to us
Basically. I don't think it's lay. Tangent lines lie below the curve. That's what I'm trying to tell you. The second derivative, if it's positive, tells you the first derivative is increasing, which means the slopes of the original function are getting larger, which means, pow, concave up. If the second derivative is positive, you now know the curve has a concave up appearance. That's the idea. I'm just trying to tell you why it should even tell you that. Why should the second derivative tell you about concavity? Because of the chain of implications I wrote here.
Depending on the slope getting better, would that make the curve become more, is it like structured strength or?
Well, if they're getting large fast, then it's going to be more like that,
Yeah, that's
right?
what I mean. Like, and then
That's correct.
based,
If they're getting larger faster, this will be more compact, right? If it's getting larger slower, then it will be more flattened out. That's true. But the important thing is that the tangent lines lie below, therefore giving you some sort of concave upwardness.
so the derivatives we do find is the rate change for the entire slope of the curve, right?
That's correct.
And then that would just tell you the rate of change in the slopes of the entire.
The second one?
Yeah.
That's right. That's exactly what we're saying. That's exactly what I'm. Yeah, that's right. Yep. So now, if the slopes are getting smaller, then that means if you started same basic direction, right? But now, if you map it out, more like like that. So then, yeah, they're getting all smaller, right? See, this one starts out around 0, and then as you move down the curve, right, the tangent lines, construct them all. They're becoming more and more negative. Smaller means number line smaller, right? Becoming more negative. So you have a concave downward appearance for the shape of the curve, which means tangent lines lie above the curve.
Does concavity have to do anything with like stretch or strength when it comes to? Because
Only the sharpness of its concavity. Yeah. Above. All right, any questions so far? So that is why the second derivative tells you what it tells you. So now, when you test for concavity, the basic process is extremely similar to the first derivative test for max and min values, right?
Is it similar?
It's extremely similar. It's the same process. It's really the same process.
So it's like going from negative.
Well, similar because you're dealing with a different derivative. That's all.
Oh.
But sin equals 0, we're finding out we're undefined, doing the test cases on the interval. All that process is exactly the same. You're just going to do it to the second derivative now. And it tells you different information. Instead of telling you possible maxes and mins, it tells you concavity and changes in concavity. So since you could have a change in concavity, that's what an inflection point is. An inflection point is important that it's a point on the curve. It's a point on the curve where the concavity changes. Okay? So it has to be on the curve. It can't just be anything. It can't just be a change in concavity. It's going to be a change in concavity where the function exists. And then it's called an inflection point. Just because the concavity changes does not make an inflection point, right?